I want to make my first couple of videos on Stokes formula, exactness of forms, especially the Poincare lemma, and the implicit function theorem, which is the topic of this video. The purpose of these videos is to develop the sufficient background knowledge to tackle the difficulties that may arise in the following videos later that I have a plan on making on thermodynamics and entropy. There will be no rigorous mathematical terms or derivations. We will just state the theorems with as much clarity as possible and move on. So we start with the implicit function theorem.
Throughout this video, we will try to find answers to these questions. We will start with the first one and go over to the second one at the very end of this video.
First, let's see why and how implicit function theorem is useful. It has wide range of applicability. I'm going to show its use, particularly in determining a family of curves in 2D plane. Let's say we have a function f with two inputs and the output is a constant. And for each such chosen constant, we get different curves in the xy plane through expressing the variable y with respect to the variable x. And we also assume that these functions or curves exhibit the same behavior in the xy plane and they are non-intersecting, not at least on our points of interest. Then roughly we can call these curves or functions to be family of curves. The equation of a circle is a good example to start with because it is trivial to express y as a function of x, and we can plot different distinct curves for different constants and they all exhibit the same behaviors, that is they are all circles and they don't intersect each other. Not all the implicit functions that we encounter in our life are going to be this easy and trivial. For example, we have a function f equals for this function there is no trivial way to express the variable y as a function of x. We don't even know whether such a function g of x exists. That's where implicit function theorem comes into play. Although it doesn't help us find out the function g of x itself, rather it helps us find all the necessary information that we need of this function, such as its existence, its uniqueness, its differentiability, etc. We will come back to this function later in this video and analyze this function very rigorously once we have had a good grasp on our implicit function theorem. Here's a formal description of the theorem. We have a function f that takes a vector having n plus m components as an input and its output is also a vector having m components. Also, f is r times differentiable and its rth derivative is continuous. Next, we divide the input vector into two parts. We call the first n components to be x and the next m components to be y, and the output, which we take essentially to be constant z0 having m components. And our objective is to express y as a function of x and how many functions of such kinds really exist for a particular constant z0. Now, what it turns out through some rigorous mathematical analysis is that if this matrix is invertible, those components goes like this, where f1, f2, f3, etc. are output components of the function f. For example, f is a function taking two-dimensional vector x and three-dimensional vector y as an input and giving three-dimensional vector as an output. Those components are f1, f2, f3. Now, for this matrix to be invertible, which essentially means that the determinant of this matrix is non-zero at a particular point x0 and y0, where x0 and y0 satisfies our implicit function, then this theorem states that there exists such a function g of x that goes through this point and it is unique and r times differentiable. Now we need to clarify a few things. Let's start with uniqueness. So what do we mean when we say that a function g of x that goes through a point is unique? We assume that there are a few functions that satisfies our implicit function, and when we plot them, we might get different curves intersecting each other, and if at a particular point the matrix that we defined earlier is invertible, then what this theorem implies is that only one curve will go through this point, which in this case is G2. In other words, this point cannot be situated on the intersection points of our curves. One more thing that needs to be addressed is differentiability and continuity. The idea is quite simple for functions having one input and output, but for functions having more than one inputs and outputs, the intuition behind differentiability and continuity is not so obvious. That's why I think it's definitely worth taking a brief sidestep to go over them now. I'm going to define the derivative in a way that we are all familiar with. We define the derivative of any function f at a point p in any direction of the vector u, which is more commonly known as directional derivative, to be a limit taken with respect to a variable t. And the only time we call this function to be differentiable at that point if we can find a matrix, a unique matrix t, which when multiplied by the vector u gives us the same result, and we call this matrix to be derivative matrix. Let's start with a simple example. We know that this function is not differentiable at this point, and we are going to prove it with the idea of derivative matrix. To find the directional derivative at the point P in the positive x direction, we take the limit, and after a fair change of variables, we end up with the forward slope multiplied by h, which essentially means that the t1, which we define to be forward slope, multiplied by u, where the forward slope is the slope of this tangent line. And on the same point P, when we take the vector u to be in the negative x direction, then after taking the limit, we end up getting backward slope multiplied by negative h, where negative h is essentially our vector u, and we define the backward slope to be our matrix T2, where the backward slope is the slope of this tangent line. But it is evident from this curve that the backward slope is not equal to the forward slope. That means for two different vector u, we get two different derivative matrix, which essentially means that the function is not differentiable at that point. For more than one variable, things start to get really complicated, because this time you can have thousands of different directions. For all those vectors, we might get different derivative matrices, and the only time the function is differentiable is when all these matrices are equal. It is an impossible task to check if all those matrices are equal. Luckily, we have a theorem that makes our life easier. The theorem is as follows. If we have a function taking m-dimensional vector variable as an input and giving m-dimensional vector as an output, and if each partial derivatives of the output components with respect to the input components exists, that means they are finite and not infinite, and are continuous for all such combinations at a particular point x0, then the theorem implies that f is differentiable at x0. Now this begs the question of what it means for a multivariable function to be continuous. For any arbitrarily chosen vector v, we say that a function f is continuous at a point p if the norm of this difference vector vanishes as we make this p plus v vector tend to p by contracting the absolute value of this vector and keeping its direction fixed. Now, to check the continuity of this function, we need to calculate this norm for every possible vector v and see if the norm vanishes or not, which is again an impossible task to carry on. But there is one more theorem that we state without a proof, as usual, is that if a function is differentiable at a point, then that function is also continuous at that point, and we might use this theorem to check the continuity of functions later on. This is the derivative matrix T that I forgot to mention earlier in the video. If the function f is differentiable, then the matrix is as follows. Its elements are just the partial derivatives of the output components. It is really not that hard to derive the expression for the matrix T, but again we'll skip that. Now we are back to the function that I mentioned in the beginning. This function can be thought of as taking two variables x and y as an input and giving one variable fi as an output. First, we check the differentiability of the function, and for that we need to check the existence and the continuity of the partial derivatives. This is the expression of the partial derivatives with respect to x, which exists for all finite value of x and y, which implies its existence. Now to check the continuity of this function, we will see if it's differentiable or not. But now to check this function's differentiability, we need to go over the same process again. That means we need to check these partial derivatives, continuity and existence all over again. And this can be really tiring. We need to check continuity, hence differentiability of each of these functions. It is easy to comprehend that the first one is continuous with respect to the variable x and y, but for the second one, which is a function of both the variables, we need to again find its derivative matrix and check if the components are differentiable or not, and which will give its continuity. So we can go on and finally find that the function is actually continuous, hence this function is continuous. But we have a better observation, which is a statement that we state without a proof. Once again, is as follows: any multivariable polynomial is continuous. So this polynomial is continuous on the real space R square, and ratio of two polynomials is also continuous at the points where the denominator is non-zero. Similarly, we can say that this also is continuous, hence the derivative matrix exists as the partial derivative of the function is continuous, so the function is at least one time differentiable. Now let's use our implicit function theorem. If you recall, we stated that for a particular point, if this matrix, which is here in this case is just a 1 into 1 matrix, is invertible, that is its determinant, which is the number itself, is non-zero, then at those points we will be able to find a function g of x that will go through that point and will be at least one time differentiable, just as f is. Now the points where the matrix will be 0 are the points of our concern. So we have two cases here. This matrix will be 0 either if x equals 0 for any value of y, which is evident from this equation, or x will be non-zero, then we will end up with this equation. Now the implicit function theorem predicts that at these points, one or more than one problems could occur. They can be the points where the function g of x might not be differentiable, or they could be points where more than one curve intersect each other, etc. Now before proceeding any further, we need to clarify one thing, which is that we call a function only when for a particular input it gives only one particular output. It doesn't give more than one particular output. That means this is a function, so is this, but this as a whole is not a function, so keep that in mind. Now before actually plotting the functions, we need to clarify why we call the functions g1 and g2 that satisfies two different equations, that is equations that occurs for two different constants, family of curves. Like why g1 and g2 are family of curves, that means they are non-intersecting. Let's say we have a point x0 and y0 that satisfies the first equation, then that same point cannot possibly satisfy the second one, because if it does, then the same term will be equal to two different constants, which is not possible. So that means curves satisfying the first equation will never intersect the second one, will never intersect the curves that satisfy the second one. Now we plot the function in the Desmos app. For different values of the constant, we find different curves that are called family of curves, as they don't intersect each other, which is evident from the plots. Now if you were to analyze one single curve, we see that on the right side we have one curve or function that satisfies the equation, but on the right side we have three curves that satisfies our equation. These three equations are this, this and that. As we mentioned earlier, this curve as a whole cannot be said to be a function, because for a particular x we have to output y. but we can think of it as a connection of two curves, that is this curve and that curve merging somewhere between here. And our implicit function theorem should be able to predict the points where two curves intersect each other, and that's exactly what we're going to see. Now recall that the points at which our theorem predicts some problems that might occur, one of them being the points where x equals 0 and y can be anything, which means this is basically the y-axis. And what this theorem tells us is that if the family of curves intersects the y-axis at any point, then at that particular point we can expect some abnormal behavior of the functions. Now as we go along the y-axis to the infinity following these curves, you see that these curves do actually intersect the y-axis, but by the time they intersect their slopes become infinite, which means these functions or curves are not differentiable when they intersect the y-axis, because we call a function differentiable only when its derivative exists and is finite. So we have found our expected abnormal behavior. Next the theorem predicts problem along this line of curves. So when we plot that, there appears a blue line. Now our theorem predicts some anomalous behavior of functions to have occurred at all the points where the blue curve intersects the family of curves. And if we observe carefully for each one of the curves in the family of curves, for example we take the green one, which as we mentioned earlier can be thought of as an intersection of two curves, the curves on the upper side and the curve on the lower side intersecting somewhere in between. And at the point where the green curve intersects the blue line turns out to be the point where the upper part of the curve and the lower part of the curve merge together. That means we have two curves intersecting at that particular point, and each of these curves individually are functions, because for a particular input x we have only one output for each particular function. We call these points to be problematic because, first of all, the curves or the functions that goes through them are not unique. That is, we have two curves that goes through this point at the same time. On top of that, each of these curves has an infinite gradient at those points, that is, the functions are not differentiable at this point. So at each of these points we have two problems or anomalies according to our implicit function theorem, and we can say that the predictions of our theorem are in line with the actual plots and the results that we saw. We will finish this video with another beautiful use of this theorem. If we are given two variables x and y, both are expressed with respect to yet another two variables x and y, s and t, then can we express the variable s and t as a function of x and y? It turns out that implicit function theorem can answer that. Now if we consider the general case where x and y both are functions of s and t, where both the functions f1 and f2 are at least one time differentiable function, and we need to do a clever manipulation and arrangement of terms to use the implicit function theorem. We define the x and y as our x variable, where the x1 component equals the x variable and x2 component equals the y variable. Same goes for the variable y, and we have our implicit function f, which has two components, and z0 is the output, which is a constant zero vector, where the zero vectors corresponds to these terms. Now if you recall the implicit function theorem, see the requirements. We need this matrix to be invertible, that means its determinant not to be 0, and this matrix turns out to be this term, and at the points where this determinant is not 0, that means this inequality is satisfied, we will be able to find a function y equals g of x that will go through that point, and it will be r times differentiable same as f, where y is the vector s and t and x is the vector x and y. We consider the example we began with and analyze the points on which the determinant of the matrix is 0, and after the calculations we get this equation of the curves on which the matrix is non-invertible. Now we plot the curves. Although it's lots of curves, these are negligible when compared to the two-dimensional flat space. So we can say that we will be able to express the variable x, s and t as functions of x and y at most of the points in two-dimensional space.